I'm going to give an overview of this tool called spaceKLIP. So what is spaceKLIP? The idea is that it's a Python package to kind of help with JWST high contrast imaging, PSF subtraction, reduction, and analysis. At the moment, we host it on GitHub at this particular GitHub link under the Space Telescope kind of umbrella. We're working on getting it on PyPy so you can do an easy pip install, but there's a lot of people have gone through installation now, so I don't think it's too tricky. If you want to learn more, you should really check out the read the docs, especially if I have to skip over some stuff today. There's a ton of information on there that you can draw from. So why not rely on the default pipeline? So Julian and Jonathan kind of summed this up a little bit throughout their talks, but the idea is that spaceKLIP is not necessarily replacing the pipeline products. You can kind of take it where you want it, but it's a way to enhance those products and get some science results straight out at the end. So that's things like control over your pre-subtraction image cleaning and reductions, greater customization over your PSF subtractions using PSF libraries, routines for contrast estimation and companion fitting. So things that actually get you science, things to put in your paper right at the end. So today I'm going to give you sort of a live walkthrough in slides of how spaceKLIP works for these 4 notebooks that are on the read the docs. So I put their links here. I'll try if I can to motivate the reasons. We do some certain steps, but I might have to skip over most of that just in the interest of time. You can also test this out on the JWebbinar platform, so that Jenny showed right at the start of the JWebbinar today. So there's the link. A few caveats. It only works for the NIRCam tutorial notebooks. Some of the plotting functions don't work or have like widgets that won't work in the platform, but shouldn't really break things. And the data download script that is part of the normal notebook doesn't work, but we do provide the data instead. The last thing is that a small amount of file setups required. I just sent a list of commands in the Slack channel that you can look at that help you basically set this file up, but I'll quickly blitz through it. You want to start a new terminal in the platform. If you type ls, you'll see what's in your current area. I have this extra STPSF data folder. You probably won't have that. That's fine. Then you want to make a new directory. First, I've just called mine spaceKLIP test, and I've moved into it. And then from there, we can copy all of the tutorial notebooks into your folder. We can then copy a couple of reference files for the stellar information into the folder. Then we can copy the data into its own directory, and this is how we'll be pulling from it to run the notebook. And then if you haven't already, you also need to set this STPSF data that Jenny showed right at the start. So not too tricky, just a handful of commands. And then once you've done that, you should have something that looks like this. And you can click and open these notebooks. Remember, only the NIRCam ones will really work, and you can get running. So with that set up, I'll try and blitz through what spaceKLIP can do. So as I mentioned, it kind of covers an end-to-end, but with different ways to sort of interact with it. And the main thing really is that, you know, you start with some user input, and this gets loaded into a spaceKLIP database. And this could be at different stages. You could start right at the most basic files you can pull from MAST and start with the data reduction, or you could start with maybe the calibrated files off MAST and then go straight to sort of image cleaning or maybe PSF subtraction. And move around this circle in a way to get science results. This can be a bit tricky to kind of appreciate all in one go. So I'm kind of going to break it down throughout the talk. So first, I'll just focus on this database concept. So we need some data to load in, and just to make the code work smoothly, we have everything interact with this kind of central core. And you're constantly editing this core, saving files from the current state of that core to move through the reduction process. So for this tutorial, we'll use the ERS data that you've seen, where we have this nice planetary mass companion here in the bottom left, or just at the bottom left of the star. So to do this, we have to, define a root directory. This is the now data download script. This is what you won't need if you're running on the platform, but if you're running things locally, you want to make some directories to just store your data in. We've built this like pre-computed command that you can just run and run the query, and it should just download the data to that folder, and off you go. Then from there, oh yeah, and I just mentioned as a reminder, you don't need to do this on the platform, that cell 4. But from there, you can load things into a database. So here we're just selecting one filter to look at. For this data we downloaded, there's actually 5 different filters. And if we were to run spaceKLIP, it would happily handle that, but it would run all 5 in a row, and that might slow things down. So just for the tutorial, we'll just look at one, this F444. And we run this command, spaceKLIP create database. We kind of just telling it where our input directory is, where our output directory is. It's filtering over the filter we've given it, and we've told it what proposal ID to look for. And then you can see everything gets loaded in into this nice AstroPy table. It's telling us a bunch of information about all of the files we've loaded in, which ones it knows are science images, which ones it knows are reference images, the kind of stage of the data that it's at, the role of the telescope at the time, and a bunch of like pre-populated columns that are just generally useful throughout the reduction and analysis process. So from there, we can start reducing the data. So if we go straight from the database to the data reduction, we're going to leverage pretty much entirely the JWST pipeline, with a few tweaks here and there that spaceKLIP has made to just smooth things over or add additional functionality for ourselves, like 1/f noise removal or some ramp fitting changes for MIRI. And that's run in this big function, which is basically just a wrapper to the JWST pipeline called Coron1 pipeline. And you can see all of these steps you can set and adjust and change. We don't have time to go through all of these today, but if you check out the read the docs for this notebook, you'll see descriptions and links for each of these steps. So you can walk through and try and build an understanding of what exactly is being done to the data step by step. But the idea is that you run that, you get your data reduced, and spaceKLIP has this sort of nice plotting function now to kind of compare. So we can take a look at what the data look like, and we can see here is our unsubtracted PSF right in the middle and zoomed in on the left. And then there's some other stuff we're seeing in this image as well. In orange, we have all of these flagged do not use pixels. So these are things that we don't trust, I guess, from the telescope perspective in terms of the quality of the data in those pixels. And then you can also see some sort of astrophysical sources in the image as well. These kind of like 6-pointed sources. So with that, obviously this looks a bit messy. I mean, maybe we want to handle these do not use pixels in a certain way. There's also some bright pixels hanging around that maybe could be sort of cosmic rays that are left over and we might want to correct. So that's where we kind of go to the next stage, to the Coron2 pipeline. So we run this. This is sort of, again, the default JWST pipeline has a few different steps. We've also pulled forward this outlier detection step from stage 3 to run right now in the Coron2 pipeline. And then we can look at sort of a left-by-left comparison and see that, okay, we've subtracted the background more easily, or we've subtracted the background so it's more easy to see these sort of sources kicking around in the image. You can also see these neutral density squares start to pop out from NIRCam. This is just a feature of the data itself. And, our counts are now changed from sort of data numbers to some actual physical unit that's useful for us to look at. Okay, so one quick note I wanted to add is that NIRCam data looks very different to MIRI, so don't expect very similar results at this stage. The glow stick really does bias things. So with the data at that stage, we can think about sort of cleaning it up a little bit and getting it ready for PSF subtraction using our image tools package. So we're going to create a database again. In this case, you don't always have to do this. You can carry on with your database that you already have, but this can be a nice way to kind of press pause on a reduction, hand it off to someone else, or when you're happy with a certain part of it, just lock it up and then start a new notebook to work on things. It's kind of personal preference how you want to run it. But you can see some of the information has changed. It now knows the data is at stage 2. It knows what the units of the image are, and some other things that are hidden in this. It's a sort of short printout. Okay, so then we can move to image tools, and this is sort of a general purpose library of functions. This includes things like median subtraction, bad pixel cleaning, MIRI background subtraction, image alignment, which is very important for PSF subtraction, and a bunch of convenience functions for sort of padding, co-adding, blurring, cropping, all that kind of stuff. And it's very easy for you to add your own functions in between as well. So the idea is it's very modular. You kind of load your database into this image tools object, and you can just hack away at all of the data until you're happy to move to the next stage. So here's a sort of example of this. We can do a median subtraction where we can specify the files we care about. We can make a comparison with this quick function here. And you see, okay, we've managed to do a median subtraction. Now the background is more evenly dispersed around 0, and all of our astrophysical sources are much clearer. This is kind of useful for CLIP particularly. The CLIP algorithm relies on things being median subtracted, so it's a nice step to do. Next, we could do some bad pixel cleaning. I won't go over this into too much detail because we could really get in the weeds, but there's things like spatial cleaning of outliers, temporal outliers, custom cleaning of individual pixels that you want to clean. And then we can set all these parameters for these different methods in this fix bad pixels function. Again, you should really take a look at the API to see how this all works. We're also planning maybe some updates to this in the tutorials in the next month or so. But you can see how that looks like here. We have all of these orange do not use pixels and maybe some bright pixels in there as well. And then we've tried to kind of interpolate to smooth this out and make our image a little more cleaner to look at. This will help with the alignment because it's very difficult to align images that have sort of nan pixels in them. For MIRI background subtraction, we have this as well. So we have this nice subtract background Godoy, which was developed by Nicholas Godoy. And you can see we can get the background images, scale them appropriately, and subtract them from the data to kind of leave behind our image to look at. With the nice stellar PSF there and not too much residual noise. And then the final example I'll give is sort of recentering alignment. This is really important for Coronagraphy because it can improve your contrast and improve your ability to detect companions. So we do this in 2 steps at the moment. We do recentering and aligning. The goal of the recentering frame is to find out where the star is in the image. You know where the coronagraph is because it doesn't move, but the star can sort of shift around behind the mask depending on how good your target acquisition is. So we do this through some sort of model fitting, and you can kind of see an image like this here, where we build the science frame, we build our model PSF, and then we can measure more precisely to around, maybe about 1/6 of a pixel where the star is. Then for aligning, we take that understanding of the absolute star position for one of the images and then do a relative sort of shifting of all of the other images to find out relatively one to another how offset or aligned they are. And you can see some examples here. So for our science frame, all of the science images at this one position are very well aligned. And then we have a different roll here where they're slightly offset. So there's about a 1/6 of a pixel shift between those 2 rolls. And then we have the reference frame alignment here, where we have these kind of anomaly where we thought the shift alignment should be, and then where we ended up measuring it. So here we can see that the pattern is relatively preserved, that small grid dither pattern, but there is some absolute offset in the target acquisition that's something we have to deal with. So you can take a look at what this looks like again with the sort of plotting function. So here we can see on the left, this is our original image, and we can see that the kind of star is not really aligned in the center of our image. So recentering takes that stellar position and shifts things to get it right in the center of the image where we want it. And then by aligning all the relative images and doing a simple subtraction, we can see that a lot of this extra noise is suppressed, and you can start to pull out the planet itself there. We can do much better with a more robust subtraction algorithm like CLIP. But for now, this is at least a nice initial indication that your alignment is going well and you're ready for that PSF subtraction. One caveat for MIRI is that we found that image alignment is not always beneficial. I've seen cases where it's useful and cases where it's really not. And the kind of reason for this is that for the MIRI PSF, it's much, much more sensitive to misalignments behind the coronagraph. And then translations of that PSF do not necessarily equal translations of the star. And you can see an example of that here for MIRI, where we have just slightly different positions behind the coronagraph of exactly the same star. And you can see that the lobes have a distinct structure that you can no longer map between one and another. So you can imagine if you shifted around the image on the right, you could shift it as much as you wanted. You would never get a really nice understanding of where the star is against the one on the left, because they just have a fundamentally different structure. Sometimes it works, sometimes it doesn't. So you should kind of play around with it if you're using it. Okay, moving on. We have PyClip for the stellar subtractions. This is a really crucial part of coronagraphy analysis. We need to remove the stellar PSF and just recover the planets, hopefully, underneath. So we leverage PyClip for this. I won't touch on this too much, but this is kind of does all the heavy lifting, all the algorithmic work for these kind of subtractions. It has its own read the docs and its own Git repo that you can take a look at. So we have a simple kind of function to run the PSF subtraction using PyClip pipeline. So in here we have some different ways to adjust with the pipeline. I'll leave this for the tutorial for you to look at, but here we can run the subtraction. I did touch on a few, so annuli and subsections. This lets you kind of split your subtraction into annular, into radial regions. It's going to help if you want to optimize your subtraction in certain areas, and the same for annular regions. The mode gives you sort of different ways to do things, and I'll link this nice review if you're really new to things that you can take a look at. Number of basis vectors. I'm not going to get into this right now, we don't have time, but take a look at the review if you want to understand. But we can then run that function and see our PSF subtracted product. And now we can see the planets really nicely popped out. We've suppressed all of that stellar flux. It looks like there may be some little bit of residual noise that we could improve with a better back pixel cleaning. And then some of these really faint sources are now much easier to see as well. Then the last stage is the analysis tools stage. So this is where we can take that PSF subtracted image and actually get some science measurements from it. So far we've been working with these two notebooks, and I just wanted to briefly mention that now we're switching to the other two, the contrast analyses notebooks. So just keep that in mind. So we want to start a new database as we switch notebook. And again, this is also kind of set up the same way. You load all the files you're interested in and load them into the database. We now know it's a PyClip file, it's at stage 3. We have information on the subtraction, etc., etc. So analysis tools is similar to image tools, and there's a few different things you can do, and you initialize it by loading the database into it. It lets you do sort of contrast curve calculations and companion extraction and fitting. So importantly, this stage relies on a stellar model. So this can be a VOT file from the Visio photometry viewer. It's at this link, or your own stellar model with 2 columns of wavelength in microns and flux in Jansky. And examples of both are provided in spaceKLIP in this sources and tutorials folder. And I also got you to copy it over on the platform. So if you're using the platform, you should already have it if you followed those commands I said. So with that, we can compute raw contrast. We're just calling analysis tools raw contrast. We're telling it about the stellar photometry, information on the star. We tell it where some companions are if we want to mask them. Here we haven't done the best job. You know, we could be masking these things out here as well. But just for a tutorial, you can kind of see how it works. And then the outspit at the end is these raw contrasts that give us an understanding of, you know, what kind of intensity of a companion we could detect relative to the star as a function of separation. Masking is a little different for MIRI because of the 4-quadrant phase mask edges. We have these kind of like bar setups to mask those edges so we don't bias the contrast measurement. So just keep that in mind if you're using spaceKLIP for MIRI data. And then we want to take those raw contrasts and compute calibrated contrasts. So for those that are unfamiliar, the idea here is that by applying CLIP, we might not do a perfect subtraction of the star, and we might actually subtract some companion flux as well. And that could bias our estimates of any flux that we measure for that companion. And in turn, bias our contrast measurements and make us think that we're overly optimistic in terms of the contrast we can reach. Fortunately, we can model this by injecting companions, performing CLIP, and then measuring the difference in the flux before and after subtraction as a function of position and separation. And we do that with this function here, similar to the others, calibrate contrast. We tell it the directory of our raw contrasts. We tell it where we want to mask. This is where we want to inject. We put a very small number of separations and PAs for this tutorial just to get it working. And then some options for the number of injections per recovery. So we can run that, and you can see that we have some throughput that kind of changes as a function of separation, and then we can correct the contrasts accordingly. And this is kind of the final contrast product you would want to show in a paper. This is the most accurate representation of your signal-to-noise limits. You can also grab the contrast for later if you want to make your own plots. They're saved in these MP files. And now we can move to the final stage in the last couple of minutes, companion extraction and fitting. You know, we're curious how bright, the position angle, separation, the noise of the image. So we can kind of set up some understanding of the star errors. I won't touch on that now, but you could do that by some photometric fitting. And then we run this big function, extract companion. So, you know, we're telling it information on the companion, the star, options for the fitting, which you can all learn about in the read the docs tutorials and the API, which KL mode you want to use this to do this fitting, some options for injecting or subtracting the companion afterwards, and then file outputs. And then voila, you run this, you get some data. It builds a model of the PSF using WebPSF, and then does a fit to optimize the position and the flux and the noise in the image. That gives you this MCMC output where you can kind of see this. So we also have capability for nested sampling if you prefer that, or if you want to explore both. It's really up to you and the kind of data you're looking at. But then these give you these final values. You know, we know now the RA and the DEC of the companion relative to the star. So that gives you astrometric measurements that you can use for orbit fitting. And we have flux measurements that you can start to use for atmospheric model fitting as well. That's kind of where spaceKLIP stops. From there, you have, you know, your astrometry, your photometry. You can go off and report detections, companions, model fits, etc. But hopefully, you kind of have an appreciation of how everything works now. It's kind of this workflow. You load into a database, and then depending on where your data's at, you can interact with these different modules of spaceKLIP to push you forwards through the process. We have some additional capabilities coming up. I won't really touch on these because I'm already over the hour, but you can take a look at these if you're interested. And yeah, thanks for coming. You can find all the notebooks here again. And my final note will be, if you have any issues or want to recommend enhancements, please make a GitHub issue or submit the help desk ticket, and we'll do our best to help you out.